Hello, we are Group 1 Intelligent Electrical Vehicle Charger. I am Cameron Breckenridge.
I'm Blaine Van Dyke. I'm Tyler Howe.
The Intelligent Electric Vehicle Charger is designed to work with the Nissan Leaf as an opportunity charger, which means it is powered from a standard wall outlet and provides the capability to top off the battery. At the top level, the design consists of 5 main sections: power electronics, sensors, control circuits, programming, and user interface. The power electronics handle the power conversion and regulation. The sensors provide information about the input and output power. The control circuits are used to control and configure the state of the charger, and the programming configures the application and microcontroller to provide usability. The user interface allows the user to communicate with the control electronics and sensors and configure the charger. The Intelligent Electric Vehicle Charger also provides the user with a PC configurable interface to control the time of day charging and view the voltage, current, and power measurements. The Intelligent Electric Vehicle Charger also uses a wireless Zigbee communication to interface with the PC application.
The charger gets its power from a standard 120-volt wall outlet. From there, the power is sent straight into the circuit breaker. The purpose of the circuit breaker is to stop the circuit when there is too much current flowing through the device. The excessive amount of current does not only damage the other components, but infringes on a number of safety protocols that our product must abide by. The connection is set up in such a way that if a spike in current occurs, the rest of the high voltage components will be safe. The power from the circuit breaker leads into the AC to AC converter. The AC-AC converter block has a twofold purpose. First, the block must electrically isolate the output of the charger from the input. This provides a layer of safety that will prevent a large output voltage from being easily shorted to ground. Second, the block must provide a step-down AC voltage to be rectified to power the microcontroller. After the converter, the power is sent to 2 components in parallel, the AC to DC converter and the contactor. The AC to DC converter block is designed to power the contactor, input sensor, output sensor, Zigbee wireless transceiver, oscillator, and the microcontroller. The output of the AC to DC block is 2 separate regulated voltages at 3.3 volts and 5 volts. The input to the microcontroller, input sensor, output sensor, and Zigbee device is 3.3 volts. The input to the contactor is 5 volts. Included in this circuit is a safety precaution that will eliminate any residual voltage once the power is turned off. The block also incorporates an LED to indicate when the power is on. The function behind the contactor block is to provide a method for the microcontroller to have control over when the charger charges. There are numerous functions of the charger that we want to be able to provide control for. To accomplish this functionality, the microcontroller sends either a signal that will trigger a contactor to connect the circuit and begin charging. After the contactor is activated by the microcontroller circuit, it closes and the power is sent to the connector which plugs into the Nissan Leaf to charge it.
The SAE J1772 connector has been chosen as a standard for charging electric vehicles in the United States. To ensure compliance with the project requirement of charging a Nissan Leaf, the Intelligent Electric Vehicle Charger implements this connector standard. As a result, the IEVC can charge not only the Leaf, but also any other vehicle that conforms to the J1772 standard. This includes the Chevrolet Volt and Toyota Prius plug-in hybrids. The Intelligent Electric Vehicle Charger is controlled from a central Texas Instruments MSP430F248 microcontroller. The microcontroller receives charging schedules and requests for harmonic data over the Zigbee wireless interface via its UART communication capabilities. A 12-bit SAR analog to digital converter receives signals from the input and output current sensors and the output voltage sensor, then translates them into data readable by the microcontroller. To measure frequency, the microcontroller's comparator is used to detect 0 crossings of the input waveform, and a timer measures the time between the crossings. Finally, the MSP430 controls the contactor state and receives inputs from the override button via 2 general-purpose I/O ports.
The programming for the Intelligent Electric Vehicle Charger is used in 2 locations, the PC application and the microcontroller. The PC application is written in C# and uses a USB Zigbee adapter to achieve communication with the microcontroller. The The microcontroller code is written in C and is connected to a serial Zigbee adapter. Thus, from the perspective of the programs, there is simply a serial data line connecting them. This allows the code to remain simple, while the wireless communication is handled by the adapters. Communication occurs between the microcontroller and the PC in both directions. The microcontroller sends the PC periodic updates on its sensor readings, charger state, and system time, while the PC sends the microcontroller information related to the charging schedule and requests for things such as harmonics or charging state. These requests are generated by the PC application when the user clicks on one of the buttons on the interface. A command code is designated for each button, and the microcontroller performs different tasks based on the code. In particular, when the microcontroller receives a request to read the harmonics, it uses its onboard analog-to-digital converter and samples the input current at a high frequency. The A to C data is buffered on the microcontroller and then sent to the PC, where the data is then sent to a MATLAB script and the harmonics and total harmonic distortion are calculated. In addition to hardware safety features, extra safety features are included in the software to provide the last line of defense. The program will disengage the charger if the frequency measurement indicates the grid is too stressed to continue charging, or if the input current is higher than 12 amps. In addition, the charger is on or off based on the charging schedule and current system time. Over here on the computer, we have the Intelligent Electric Vehicle Charger interface. On the left, you can configure the charging schedule with the start and stop time of the charger. On the right, it displays the current charger system time. So the difference is taken between the computer system time and the charger and displayed. So they're exactly in sync right now. In the lower right, the current charger state is displayed. Right now the charger is off. So if we set the schedule to start at 150 and turn off at 152, actually let's turn it off at 151 and 30 seconds. It'll turn on the charger, and then in about 30 seconds it'll turn it back off. And while we're looking at that, we can compare the input and output data to what we display on the screen. So right now it's outputting 113 volts to our simulated load. On the PC interface, it reads 1.1 volts, which is within the tolerance of our specifications. It's also outputting 7 amps. And at 151 and 30 seconds, the charger turned back off. And it's no longer displaying an output voltage.
The Intelligent Electric Vehicle Charger is equipped with sensors for input current, input frequency, output current, output voltage, and output power. The PC program displays these values in an easy-to-read manner. The input and output current sensors are Hall effect sensors, which serve to maintain isolation between the power and microcontroller sections of the charger. The input frequency sensor is used to measure grid frequency and determine stress conditions, and the output voltage is used to calculate output power.
So for this portion of the demonstration, we'll be representing the harmonics and the total harmonic distortion. In order to do that, we press the represent harmonic data button, and then we wait for the progress bar to complete. Now on this interface, you see we have the current. We describe the current in amps and for each harmonic, and then we describe the I-squared value so that it's easier to demonstrate the total harmonic distortion, and then we represent the percent of the total, percent of the fundamental harmonic. Now, the reason we calculate harmonics is so we can measure the distortion of the waveform. Basically what a harmonic is a separation of a distorted waveform into different sinusoids at different frequencies. So here's the representation of the harmonics. So this concludes our presentation on the Intelligent Electric Vehicle Charger. Now we have some hints for next year's seniors. The biggest thing that
I came up with when doing this was we purchased the wrong size components for a lot of our chips, so that soldering it was a real pain. So make sure that you know exactly what size. Don't get HTSSOP unless you know for sure that you have the circuit board for it.
Another problem we ran into was we picked out our microcontroller before we knew exactly what requirements we needed to meet. So be sure that you know the size of RAM on your microcontroller and the types of inputs and outputs that it needs before you pick out the chip that you're going to use for your microcontroller.
Be sure you're aware of the power state of your device before making any modifications to the interior to avoid unintentional arcing.
This concludes our presentation of the Intelligent Electric Vehicle Charger.